Every morning, at industrial depots worldwide, fleet managers and drivers walk around their delivery vans to visually inspect the tires before routes commence. But a 5 PSI pressure deficit on a modern commercial van tire goes entirely unnoticed by the human eye during these routine checks. The tire appears perfectly round and capable of carrying a full payload. Beneath the surface, however, that slight drop in pressure initiates severe thermodynamic drag. Telemetry logging from loaded delivery routes captures the precise consequence: a continuous 1.8 to 2.3% fuel burn penalty over the course of a standard shift. Relying on visual inspections creates a dangerous operational blind spot. This invisible squish bleeds hundreds of liters of diesel per vehicle annually, regardless of how stable the tire looks from the outside. To locate where that diesel is being wasted, we have to look past the macroscopic vehicle and examine the microscopic contact patch where the rubber meets the road. This diagram isolates the physical deformation. On the left, a tire inflated to 65 psi maintains a uniform contact patch. When pressure drops to 60 psi, the tread's center buckles inward. The payload weight displaces to the outer edges, overloading the shoulders and forcing the sidewall to bulge outward. This geometric distortion acts as a physical catalyst. By forcing the tire to buckle and bulge, it actively increases the vehicle's mechanical rolling resistance. Commercial tire rubber is a viscoelastic material. It exhibits both viscous and elastic characteristics simultaneously when subjected to mechanical deformation. During every rotation, the tire carcass compresses heavily entering the contact patch and rebounds exiting. The under-pressurized bulge forces an extreme cycle of compression and expansion. Due to its viscoelastic nature, the elastic strain energy fails to fully recover during rebound. This failure to rebound is quantified as hysteretic energy dissipation. The trapped energy does not simply vanish. It dissipates entirely into the rubber as unrecoverable thermodynamic heat. This hysteretic heat generation actively fights the forward momentum of the vehicle, acting as a parasitic mechanical drag on the entire system. A 5 psi deficit increases the tire's coefficient of rolling resistance by a strict 5 to 7%. To overcome this elevated drag, the vehicle's engine management system must rapidly compensate. The powertrain is forced to continuously output additional shaft torque just to maintain baseline cruising speeds. Telemetry data logged from loaded 3.5-ton delivery vans operating Ford Transits and Mercedes-Benz Sprinters tracks this mechanical burden in real time. That extra shaft torque requirement is the direct source of the continuous 1.8 to 2.3% fuel burn penalty across standard multi-drop and highway routes. A portion of the fleet's diesel budget never moves a single piece of cargo. It is burned entirely on forcing the engine to fight the deformed shape of its own tires. This mechanical stress compounds dramatically when the van moves from suburban stop-and-go routes to a sustained highway cruising speed of 90 kilometers per hour. At this velocity, the tire undergoes roughly 750 to 800 compression cycles every single minute. The internal architecture of the tire, the radial steel belts, the polyester cord body, and the butyl inner liner must withstand this rapid flexing. The deep sidewall bulging caused by underinflation forces these distinct structural layers to violently rub against one another under the weight of the payload. This destructive internal grinding generates aggressive interply shear friction. At 800 cycles per minute, this interply shear friction acts as an internal furnace, converting mechanical motion directly into rapidly escalating core temperatures. This flowchart tracks the exact chain reaction, mapping the progression from underinflation down to severe internal core temperature escalation. Fed by friction, the core temperature inside the tire climbs rapidly from 85 degrees Celsius to well over 105 degrees. When those core temperatures sustain above 90 degrees, the rubber compound crosses a critical threshold, moving from running hot to actively experiencing thermal degradation. This triggers distinct structural failures deep inside the casing, including carcass rubber vulcanization breakdown and belt edge ply separation. A secondary casualty of this process is accelerated shoulder scrub, which physically strips away 18% of the tire's total tread life. The thermal cascade creates a permanently compromised casing. The degraded rubber is unsuitable for retreading and drastically heightens blowout risk when operating under full payload. We can calculate the total financial destruction of these micromechanical failures by looking at the impact on a standard commercial delivery van running 45,000 kilometers per year. This matrix quantifies the exact damage. A nominal 65 psi serves as baseline. Drop pressure by 5 psi, 98 liters of wasted diesel and 8,000 kilometers of tread permanently lost. At a 10 psi deficit, loss accelerates. At a 15 psi drop, extreme heat guarantees premature casing failure. The financial damage of underinflation does not scale linearly, it scales exponentially, aggressively eroding fleet margins with every single uncalibrated tire in the depot. To sever this parasitic draw and protect operating margins, fleets must implement strict, data-driven protocols. First, mandate cold calibration. 30 minutes of driving creates thermal expansion, masking a dangerous cold pressure deficit. Second, deploy direct valve cap telemetry. Automated sensors intercept core temperature escalation before catastrophic delamination. Finally, dynamic axle load balancing. Pressures must be adjusted to prevent sidewall bottoming during high-speed transit. Modern fleets must abandon the visual walkaround. Defending operating margins against the absolute thermodynamic reality of underinflation now requires rigorous, real-time telemetry.